We talked about kinetic molecular theory and how gas particles travel in a straight line until they run into something. So how far do they travel between collisions? They can collide with each other or with the walls of the container. The distance on average between collisions is called the mean free path. So their free path, mean meaning average. So that mean free path is going to decrease as the pressure increases because the gas particles are going to be closer together. So they're not going to be able to travel as far before they run into something. Just to sort of give you some reference, if a nitrogen molecule was the size of a golf ball, it would travel about 40 feet before it runs into anything. So that's actually quite a long ways, isn't it? So we can imagine the gas molecules bouncing around inside this container. Mean free path is how far they can go without running into something. We know that gases spread out, right? I've got a lot of sons, and so there's a lot of farting that happens in my house, right? And so, you hear the noise, and then you smell the smell, right? Because it's a gas, and it moves, it spreads, right? The process by which gases spread out from that high concentration to a lower concentration is called diffusion. And diffusion happens because the particles are moving in a straight line until they run into something. Heavier particles are going to diffuse more slowly than small particles. Why is that? How fast are they moving? Slower. Big particles move slower. Small particles move faster. So heavier particles diffuse more slowly. Gases can also escape from their container through a small hole. And when they escape through a small hole into a vacuum, this is called effusion. So the rates of diffusion and effusion are both related to the speed of the particles, the root mean square velocity of the gas particles. So at the same temperature, the rate of gas movement is going to be inversely proportional to the square root of the molar mass. Larger particle, slower movement, slower diffusion. So that brings us to Graham's law of effusion. For two different gases at the same temperature, the ratio of their rates of effusion is given by this equation. The rate of gas A compared to the rate of gas B is equal to the square root of their molar mass ratio, but the molar mass ratio is upside down. It's inverted. So gas A was on top over here. It's on the bottom over here. And this comes, I'm not doing the derivation for you because I didn't think you'd be all that interested. This comes from kinetic energy being equal to 1/2 mv squared. So the kinetic energy is directly proportional to the mass, and it's proportional to the square of the velocity, and the rate is related to the velocity, and so that's why we've got a square root of molar mass here. Fast particle has large molar mass. Slow particle has high molar mass, and that's why it's inverted. So that's Graham's law of effusion. Here's a picture of effusion. Here we've got a divided box containing gas particles, and the gas particles are going to just bounce around in this box. There's a hole. Come on, pointer. Participate here. There you go. There's a hole right there in the wall. And on this side, originally there's a vacuum. There's no gas present. And so we might think of that vacuum as like sucking the gas out. But that's not what happens. A vacuum is just nothing. It can't suck gas out. What happens is these gas particles are going to bounce around until they happen to make a direct hit on the hole, and then they're going to go through. Once it goes through the hole, it's just going to bounce around on this side. Now, the chances of gas particles hitting the hole and going back the other way are much smaller because there's very few gas particles over here. There's a whole bunch over here. But it's just a random happening to hit the hole that causes the effusion. Now, the faster the particles are moving, the more likely it is that gas particles will hit the hole and make it through. Any questions? This question tells us to find the ratio of effusion rates of hydrogen gas and krypton gas. So we're going to need Graham's law of effusion. And that was the rate of A over the rate of B is equal to the square root of the molar mass of B divided by the molar mass of A. So what's the molar mass of hydrogen? Well, one mole of atoms is 1.008, but we need to remember that hydrogen is a diatomic element. Yeah, so that's going to be 2.016 grams per mole. And then krypton, 83.80. So when I get a ratio, I like the ratio to be larger than 1. So it doesn't necessarily have to be hydrogen to krypton or krypton to hydrogen. The question doesn't specify. I'd like to put the faster rate on top, just because that's what I like. Which is going to be moving faster, the hydrogen or the krypton? Hydrogen. The small ones move quick, and the big guys are slow, right? So I'm going to put rate of hydrogen on top and rate of krypton down below. So then over here, I'm going to put the molar mass of krypton on top. And the molar mass of hydrogen underneath. And so that ratio is the square root of that. Square root of 83.8 divided by 2.016. So 6.447. Notice that the units cancel out here. The ratio doesn't have any units. So this ratio of 6.447 tells me that hydrogen effuses almost 6.5 times faster than krypton does. Any questions? Effusion, although not technically the process by which helium balloons go flat, is very similar to that. So a helium balloon, you fill it up and it floats and everyone's happy, right? And then as time goes on, the balloon gets smaller and doesn't float anymore, and a couple days later it's just laying on the floor, right? What happened? Where did the helium go? Well, the balloon has little tiny holes in it. And helium is a very small atom, and it can get through those holes. And so as the helium atoms are bouncing around inside the balloon, they will occasionally hit one of those little tiny holes, direct hit, and the helium will leave the balloon. So if you filled the balloon with a heavier gas, it wouldn't float, but it would stay inflated longer because those gas particles would escape more slowly. And it's not that they don't fit through the holes, it's that they just move more slowly. Any questions?